I've been waiting all week to show you this one. We're finally breaking down the new workflow. And honestly, it's kind of a game changer. Let's dive in.
You know, everyone's been asking me how I'm getting these results lately. And for a long time, I didn't have a simple answer for you. But after weeks of troubleshooting, breaking the code, and honestly, almost giving up on this project entirely, I finally found the missing link in the workflow.
So this is the InfiniteTalk workflow running on ComfyUI. And today I'm going to break down every single node in this workflow and explain what each model is actually doing under the hood and tell you which settings matter and why. So before we dive into the nodes, let me give you a quick mental model of what this pipeline actually does at a high level. Because it's not magic, it's a very deliberate sequence of transformations. So the input is a portrait image and an audio file that contains the voice that our character is going to have. The output is a video where the person speaks with accurate lip sync, head motion, and natural expression. So this system is built on top of Wan 2.1 video model, specifically the image to video variant. InfiniteTalk, which is developed by Gen AI, adds an audio conditioning layer on top of that. It doesn't just paste a moving mouth on the face. It actually conditions the entire video generation process on the rhythm, cadence, and phoneme information from the audio that we provide. So head nods, blinks, shoulder movement, all of that gets driven by the audio. Now we're going to walk through the actual workflow. So in the audio group, we basically have to provide an audio file. You can either load an audio file that you already have. In this workflow, I'm using Qwen3 text-to-speech model to generate audio on the go. If you're interested in Qwen3 TTS, you can refer my previous video. I've made a video on this topic. So once we have the audio generated, we crop the audio to a maximum of 2 minutes long because we don't want to be generating videos that are longer than 2 minutes because of VRAM constraints and the amount of time it will take to actually generate that video. Before generating the audio embeddings, the audio separation node is used to isolate the vocals. Now this is an absolutely critical step. Background music or noise in the audio input can actually confuse the wave to VEC model, leading to a jittery or inaccurate lip sync. We then calculate the total number of frames that need to be generated by taking the audio duration and multiplying it by the frames per second. The math expression node executes the formula to ensure the latent video length matches the audio length perfectly. Now let's explore the image group. We use a standard ComfyUI image loader that loads an image from our disk. The key thing to know here is that InfiniteTalk performs best with frontal face images. Side profiles do work, but you will see more artifacts and inaccuracy in the lip sync. Avoid images where the face is very small relative to the frame as well. So in general, you want a portrait picture where the face is clearly visible and is of decent size. Then we resize the image to match the resolution that Wan video model expects. Generally, this resolution will always be a multiple of 16. We're using 384 width into 640 pixels of height, which is a 9:16 portrait mode. It's pretty standard. The models group. This is where things get technically dense. We have 6 separate models loading here. Let's start with the Wan Video Torch Compile settings. Before we even load the main model, we configure torch compilation. The first run after enabling torch compile will be slow, but every subsequent run will be significantly faster. Wan Video Block Swap. Now this is one of the most important memory management nodes in this entire workflow. It implements CPU offloading at the transformer block level. The setting blocks to swap, which is set to 15. Well, basically it means 15 of the transformers attention blocks are offloaded to CPU RAM and loaded back to the GPU on demand during a forward pass. If you run into CUDA out of memory errors, you should increase the blocks to swap setting. Now we also provide a LightX2V LoRA in this process. What it basically does is that it's a distilled LoRA that's trained to produce high quality results in as few as 4 to 10 steps instead of the standard Wan video steps, which is around 30 to 50. So without it, generating a 2-minute video at 30 frames per second might take several hours. With it, you're looking at a fraction of that. Do not set its strength to a full 1, as that can cause color shifts and reduce identity preservation. I've seen that 0.8 gives you the most speed benefit while keeping the face consistent. Now the Wan multi-talk model loader loads the InfiniteTalk model. This is a GGUF quantized version of the actual model. And you should know this is not a standalone video generator. It essentially works as an adapter on top of Wan 2.1 video. And it basically injects audio conditioning into the attention layers during the video generation process. For our use case, we're using the single person variant. There's also a multi-person variant if you need to sync multiple speakers in your video. The UMT5 Double XL text encoder model basically processes the positive and the negative prompts into text embeddings. These are then fed into the attention layers of the diffusion transformer to condition the video based on our textual description. The clip vision loader node basically encodes the reference image into a semantic embedding space. These embeddings basically tell our video model who this person is, what they look like, and how they are different from the spatial positional information that goes through the VAE. The Wave2 Vec2 model basically outputs a sequence of feature vectors that encode the acoustic characteristics of each spoken segment. Coming on to the VAE, it basically compresses the video frames into a latent space for the diffusion model and decompresses them back to pixels at the end. This is a video VAE, variational autoencoder, not a standard image VAE, meaning that it also handles temporal compression across frames, preserving motion coherence. Let's have a quick look at the settings group. Here we set the frames per second and the resolution, the width and the height of our video that we want to generate. Now let's explore the embeddings group, which handles our multimodal embeddings. The text embeddings uses the UMT5 Double XL encoder. It processes our positive prompt to define the visual context and style. The audio embeddings generated by the Wave2 Vec model is essentially lip sync. So these embeddings essentially convert the raw audio into temporal embeddings, and these embeddings guide our Wan video model about how the mouth and the lower face should deform at every millisecond in accordance with the audio. Coming over to the clip vision embeddings, this is where we pass the reference image and pass it through the clip vision model. This creates a high-level semantic representation of the person's features, and it basically ensures that the AI understands who it is animating beyond just the pixel data. When generating audio embeddings, pay attention to the audio CFG scale setting. Now you can have this set at 1, 0.8 up till 3. This basically controls how strongly our model follows the audio cues. Higher values can lead to more pronounced mouth movements and may also introduce artifacts if the audio is noisy. If you want a more expressive lip sync video output, you should consider increasing its value. Coming over to the sampling, since we're using a distilled Lightning LoRa with Wan video model, we essentially need to ensure that our CFG is set to 1. If we were not using the LoRa, the CFG would be somewhere around 5. And when it comes to steps, we only need around 7 to 10 steps for the whole generation to be completed. But if we were not using the LoRa, we would set the steps to be somewhere around 30 to 50. Our sampler essentially combines the text embeddings, the image embeddings, and the audio embeddings. It uses the Wan video model and it generates the output samples, which is decoded by the Wan VAE. Coming over to the output, we essentially combine all the images that were generated through our sampling process that were decoded into images. We combine it with the audio that we had from the input. We provide it with the frame rate that was set globally, and we have the output. The entire workflow is provided in the description. If you like this content, if it added value to you, consider liking and subscribing. Thank you. I'll see you later.